All right, here we are in a section where we're going to be talking about trigonometric equations. You worked with equations that have x's and y's and z's in them, square root functions, maybe logarithmic functions, cubes and cube roots, absolute values. All of those were functions, and we're going to mix it up a little bit. In this section, we're going to be also including trigonometric functions in equations that should look really familiar to you, like quadratic equations that you could theoretically solve using the quadratic formula, but I'm pretty sure most of those equations in this section can be solved by factoring. Hold on to your seats, this is going to get interesting. The very first and maybe most unusual thing, the newest thing that we're going to see in this section is this. And it's it's not the newest thing that you've ever seen, but it's pretty new. This equation that says sine x equals 1/2, for example, has multiple solutions. There are multiple x values that we could plug in and take the sine of and get an answer of 1/2. And here's a graphical depiction of those solutions. For example, the sine of pi over 6 is equal to 1/2. The sine of 5 pi over 6, of 13 pi over 6, 17 pi over 6. Even over to the left there, negative 7 pi over 6. All of those are solutions, because if we took the sine of any of those angle measures, the output value, the y value, would be 1/2. And there's even a horizontal line there that looks red on my screen. It's labeled y equals 1/2, so we can see those intersection points, and the x coordinates are the solutions. So the solutions on this interval, I have to turn my pen on for that to work. There we go. On this interval, the solutions are pi over 6, 5 pi over 6, 13 pi over 6, and 17 pi over 6. You can write in those solutions here and separate each one of those values by a comma. We're not including the negative 7 pi over 6 because that's not on that interval from 0 to 2 pi. We only want those 4 solutions that appear here. But what if we were prompted for all of the solutions? Remember that these trig functions, all of them, have they're all periodic in nature. So for example, the sine function has a period of 2 pi. So not only is the sine of pi over 6 equal to 1/2, but if I took pi over 6 and I added 2 pi to it, I added the period of the sine function to it, and took the sine of that resulting angle measure, which would be 13 pi over 6, 2 pi, yeah, 12, 13 pi over 6, that answer is also equal to, or the sine of that angle measure is also equal to 1/2. I'm stuttering because I'm questioning my arithmetic. Now, the pi over 6 plus 2 pi is the same thing as pi over 6 plus 12 pi over 6, which makes 13 pi over 6, which means the very first thing that I said was incorrect. The solutions, they just put this on a platter for us, and I just went to town on it. Back up. The only 2 solutions that we're seeing here that are on the interval from 0 to 2 pi are these 2 solutions, pi over 6 and 5 pi over 6. These values are larger than 2 pi, so those are not going to be included in the solution that you're writing here. Right here, you only want to be writing the pi over 6 and 5 pi over 6. Pardon my handwriting with the digital pen, and I just don't get along super well. Okay, so those are the only 2 solutions on 0 to 2 pi. Now, for all of the solutions, because of the periodic nature, we could take the pi over 6 and add multiples of 2 pi. How many multiples? Maybe n of them. We could add n 2 pi's. We could add 1 2 pi, 2 2 pi's, 3 2 pi's, 1,000 2 pi's, 1,000 full rotations, 1,000 periods of the sine function. Whatever that angle measure ends up being, take the sine of it, you'll still get an answer of 1/2. You could also subtract multiples of 2 pi. And you could do that to the 5 pi over 6 also. So we're going to express all solutions like this. Were we using an x value? Yep, sine of x equals 1/2. So I'm going to say all solutions, I'm going to use set builder notation and say that my solution set is the set of x values such that, now that's a vertical bar that I've drawn right there, it means such that, the set of x values such that x equals pi over 6 plus n times 2 pi, and then you could put a comma or you could write the word or, x equals 5 pi over 6 plus multiples of 2 pi. Now tell me about this n value. Could n be equal to 1/2 or 1/3 or the square root of 3? It can't. N needs to be an integer. So somewhere, and depending on what textbook you're using, what software you're using, who your teacher or professor is, well, all those people would probably tell you to silence your phones before you started making a recording, but other than that, the notation can be a little bit different. So what I do is I need to note that n is an integer. -3, -2, -1, 0, 1, 2, 3, right? It's like the whole numbers, but could go in the negative direction also. So we could be adding or subtracting whole number multiples of 2 pi. And I denote that by saying that n is a member of the set of integers. And remember that that Blackboard Z represents the set of integers. And I believe that the Z comes from the first letter of the German word for numbers, which I think is Zahlen. Don't quote me on that though. So that would actually be the solution to that initial problem, the sine of x equals 1/2. If we were prompted for all solutions, that would be my answer. Again, notation can vary from book to book and classroom to classroom. Let's try to find all the solutions to this problem. The tangent of x equals the square root of 3. Now the tangent problem is a little bit different because the period of the tangent function is pi instead of 2 pi. So we'll be using probably integer multiples of pi instead of 2 pi. And let's see, in the first quadrant, how do I get tangent to equal square root of 3? I think I need opposite over adjacent to be root 3 over 1, which means that that theta value or x value in this case is going to be pi over 3. Yeah. And then tangent's positive again in the third quadrant. And I could actually get to that angle measure simply by adding pi radians, because the period of the tangent function is pi. So pi over 3 plus pi would be 4 pi over 3. But this problem is actually a little bit easier because we don't need two statements in our set builder notation like we had for the sine function. In the tangent function, we can use this initial angle measure of pi over 3 and just add integer multiples of pi. And we'll keep doing these sort of half rotations around the circle. I thought my door was open, but it's not, it's closed. So our final answer on this one is going to be the set of x values such that x is equal to, we'll start at pi over 3 and then we'll add integer multiples of pi where n is a member of trying to use my good handwriting there, the set of integers. And get that bracket on there. Nice. And then you could put a box around this as a final answer. There are infinitely many solutions inside of that box right there. That's a lot of solutions. All right, let's keep going. This is a little unusual, so if this is feeling the tiniest bit uncomfortable, I'm not surprised. You're going to have to work some of these. We'll keep writing infinitely many solutions as many times as we can to get you familiar with this. This is another equation. Both of the problems that we've seen previously had equal signs in them, so there were equations. This equation just needs a little bit of preliminary work before we start writing up a final solution like we did in the previous problems. Here I'm going to subtract 3 sine theta from both sides, and if you would like to, you may put a minus 3 sine theta off to the side. That's the notation that I like to use. Just a little note about what I'm doing to both sides of the equation. The left-hand side results in a 2 sine theta. The plus 1 is still there. There's a 0 on the right-hand side. I'll subtract 1 from both sides. Now 2 sine theta is equal to negative 1. And then next I will divide both sides by 2. So that sine theta is equal to negative 1/2. And now we're sort of right back where we were in the 2 previous problems. Now we could draw a little diagram in order to figure out where the initial 2 solutions are for this equation. I know that sine is negative. Let's see, sine is opposite over hypotenuse. So sine is negative in the 3rd and 4th quadrants. So if it's helpful to you to draw a little diagram of the 3rd and 4th quadrants, don't hesitate to do that. We've got, if you want to put equals opposite over hypotenuse, if that's helpful to you. So the opposite's going to be the negative 1, and the hypotenuse is going to be the 2. So there's a negative 1 and hypotenuse of 2. Let's come down here into the 4th quadrant, get that opposite side of negative 1, hypotenuse of 2, and the reference angle that's inside of here is, since it's opposite the side length of 1 in our 30, 60, 90 triangle, that's a pi over 6. So my first theta value that's in the 3rd quadrant there, I'm going to continue doing my work over here. That first theta value is a 7 pi over 6. And the second one, all the way into the 4th quadrant, almost all the way around, it's pi over 6 short of a full rotation. Right, we've gone almost all the way around there, which makes that 11 pi over 6. And those are the 2 angle measures that we will use in a final answer that looks a lot like the very first final answer that we did at the top of page 1. So our solution set is going to be a set of, in this case, theta values, such that theta is equal to 7 pi over 6 plus integer multiples of 2 pi. Or we could have theta values equal to 11 pi over 6 plus integer multiples of 2 pi. Remembering that those n values must be integers or members of the set of integers. I've been using n. In previous sections, in previous videos, I've used the lowercase letter k. You might see that also. There you are. So when do I use pi and when do I use 2 pi? I'm using this n times 2 pi because I'm working with the sine function. If I were working with cosine or secant or cosecant, I would also be using a value of 2 pi. With tangent and cotangent, I'm going to be using pi, and I'll only have to have one statement like this instead of here where I have 2 statements. So again, tangent and cotangent are only going to have one statement in there. Is it possible that my solutions in a sine or cosine problem will be pi away from each other? I don't know. I would say no. I'm going to go, if it were equal to 0, the sine of 0 is equal to 0, the sine of pi is equal to 0, the sine of 2 pi, 3 pi, 4 pi, 5 pi is equal to 0. So that works For the sine function, that might be the only time that you would see only one of these statements, and you could use a plus n pi. That's for the sine function. For cosine, that would happen at where does that happen? Does that happen at the zeros also? Cosine goes from, I'm so visual with this kind of stuff. Cosine starts up here, down to here, back up to here. Yeah, so the distance from this intercept to this intercept is a distance of pi. So when cosine is equal to 0, you could also write up a final answer that only has one theta equals statement in it, where you'll have a plus n pi. If that just went right over your head, don't worry about it. That particular situation doesn't come up all that often. But for those of you who are finding that you're pretty savvy with this stuff and that clicked, or you'd like to go back and listen to that again and see if you can make it click, then it's there for you. So you can dive a little deeper on this particular topic or process. So we're going to change gears a little bit in this section. The next subtopic is multiple angle equations, and these are interesting. I'm going to sort of cruise back up here to the very top of these notes, and I'm going to highlight the first period of this sine function that we have here that goes from 0 to 2 pi. And the number of solutions that you're seeing in there to this particular equation, y equals sine x, sine x equals 1/2, the number of solutions that we saw are 2. And I accidentally included these two solutions in my answer the first time, but really they're not on this interval from 0 to 2 pi, so I should not have included them, and so I had to go back and change that. Is there a way that I could just kind of smush those two solutions over into that highlighted region that I just highlighted so that they do become solutions? You should know that there's absolutely, that's called a horizontal shrink. And how do I take the sine function and horizontally shrink it? Remember that we've been working with equations that say something like y equals capital A sine parentheses bx minus c plus d, and it's the b value that causes a change to the period. It causes a horizontal stretch or shrink. And how do we get a horizontal shrink? We would need the new period, remember, is equal to 2 pi in the case of the sine function, divided by b. So in order to make that 2 pi smaller, b needs to be larger than 1. So if we can make the b value large enough, we should be able to compress or horizontally shrink another couple of solutions into that highlighted region. So again, that's if the b value were greater than 1. So this is saying that if our b value is greater than 1, then we have some number of solutions, whereas if our b value is between 0 and 1, then we have some other number of solutions. I'm not willing to write those in just yet. Let's see if we can discover what goes in there for ourselves. And finally, I have my first instance of the iPad dipping out on us. Let's see if we can get it back as reliably as usual. There it is. Nice. All right, so let's see if we can find all the solutions on this interval from 0 to 2 pi. Let me show you how to do this. What I'm going to do is I'm going to call x over 2, I'm going to call that theta just for a moment. I'm going to let x over 2 equal theta so that I can write that the tangent of theta is equal to root 3 over 3. I know those don't look like 3's, so you have to be listening as you're watching. Root 3 over 3. And what are the solutions to that statement? What are all the solutions to that statement right there? Well, root 3 over 3. It's opposite over adjacent. Remember that this is also equal to 1 over root 3, pre-rationalization of the denominator. That makes more sense to me. It's more familiar. It jibes with the triangles that I've seen all semester for my entire class. So this is a theta value of pi over 6, opposite over adjacent, 1 over rad 3. So this tells me that theta is equal to pi over 6. And if I wrote out all solutions, I could say that theta is equal to pi over 6 plus integer multiples of pi. And I'm using pi because that's the period of the tangent function. Now, well, this is great. So I could plug in an n value of 0, an n value of 1, an n value of 2, and I could crank out some theta values and I'd have my answers. Problem is, we're not looking for theta values. We're supposed to be looking for x values. So at this point, now that I've gotten to this kind of generic all solutions kind of a statement, where I could just keep cranking in, plugging in n values and cranking out theta values. Once I get to that point, now I'm going to back substitute, is what I've always called it. I'm going to replace theta with x over 2. So that we get this statement, x over 2 equals pi over 6 plus n pi. Excuse me. We're trying to find x values. Look at your original equation. What's the variable? It's x. So let's solve this equation for x. I'm going to multiply both sides of this equation by 2 so that I get x equals pi over 6 times 2 is equal to pi over 3 if we simplify it. And then the multiple of 2 also has to hit that second term. So I think I'll write this as, excuse me, n2 pi. I like the 2 multiplied into the middle there, so it's next to the pi. I like seeing 2 pi because I know what that is. It's a full rotation. And now we're going to start plugging in n values and cranking out x values. You should write yourself a little note and phrase it however you want to. I'm not going to write it. You write it. We now plug in n values starting at 0 in order to generate x values. We stop plugging in n values when the x values become larger than 2 pi because we're trying to find all of the solutions on the interval that goes from 0 to 2 pi. Sophie also wants the solutions on that interval. Let's see if she's willing to... Will you come help us? Yeah? Well, come on then. This is already going to take forever. We're only on page 2. We might have to make this a multi-part video. All right, she's just going to meow for a while. So let's try an n value of 0. That gives us x equals pi over 3 plus 0 times 2 pi, and that's equal to pi over 3. I like it. That's in the interval from 0 to 2 pi. I'm putting a box around it right away so it doesn't wander off. Now let's try an n value of 1. N value of 1 gives us x equals pi over 3 plus 1, 2 pi. Ooh. Now, granted, I know what to look for, but if I'm supposed to be keeping my x values between 0 and 2 pi, well, this is 2 pi plus some more stuff. That puts me over the mark, past the mark. I'm now larger than 2 pi, which means I'm not even going to figure out what this is with a common denominator. I don't even care that it's 7 pi over 3. Okay, it's too big. Too big. Or larger than 2 pi, exclamation point. Therefore, let it go. Therefore, it's not a solution, however you want to phrase it. So our one solution to this problem is x equals pi over 3. It appears that we only have one solution instead of two solutions, which we might have anticipated. And taking our x value and dividing it by a b value of 2 cut our number of solutions in half. Oh wait, the b value is not a 2. We're supposed to be multiplying it. What this really says is the tangent of 1/2 x. So the b value is a 1/2, which is between 0 and 1. And as a result, we ended up with, I guess we could say 2 times b solutions, because 2 was our normal number of solutions. Multiply that by a b value of 1/2. 2 times 1/2 makes 1, and we only had one solution. So maybe I get rid of the s there because it's singular. 2 times b solution. If our b value is greater than 1, I wonder if we also end up with 2 times b solutions. Let's see, if my b value was greater than 1, using that format, I think we should probably do a problem like that and see what happens. Let's find another example. Now this one said the tangent of x over 2, which was the same thing as a coefficient or a b value of 1/2. In this problem, we've got a b value of 2. Okay. Well, let's try it. Let's see if we can use the exact same process as we did in the previous problem and get ourselves a solution to this one. Let's let theta equal 2x minus pi over 4. That's a 4. There we go. Now we can rewrite our equation as the sine of theta is equal to root 2 over 2. When does that happen? For which theta values? Let's find all of our solutions. Root 2 over 2, that sounds like a pi over 4 kind of a situation. So I would say that theta is equal to pi over 4 plus integer multiples of 2 pi, or theta is equal to, opposite over hypotenuse to be positive. I think that puts us in the third quadrant, or second quadrant. All students take calculus. All students. S students, sine, positive, second quadrant. Yeah, that's it. Okay, so 3 pi over 4. Do you have any solutions for us? No? Okay, keep moving then. Get out of here. You're cute, but not helpful. Plus integer multiples of 2 pi. Great, so we've gotten to that point. I think I circled it in the last problem where I have my statements that represent my infinitely many solutions, all of my solutions. Now we're going to replace theta with 2x minus pi over 4. You can write back substitute. You can write replace theta with 2x minus pi over 4, however you want to phrase it. That's how I wrote it in the previous problem. That's what I'm going to do to both of these equations. So I have 2x minus pi over 4 is equal to pi over 4 plus n times 2 pi. This is straight arithmetic from here on out. I was going to say pretty much. It's not pretty much. It's just arithmetic. Let's also replace that other theta with 2x minus pi over 4. That's equal to pi over 4. Oops, sorry, 3 pi over 4 plus integer multiples of 2 pi. And now we need to solve these equations for x, and then we'll churn through some n values. So if you want to put a little note over here that says solve these for x, you can, or we can solve it for x and then bracket it and write solve these for x. Put that note wherever you want. Let's add pi over 4 to this first equation. So we have 2x is equal to pi over 4 plus pi over 4 makes 2 pi over 4s, which reduces to pi over 2. Plus, still have our integer multiples of 2 pi. Then divide both sides of the equation by 2. That gives us x equals pi over 4 plus n pi. Let's move over to the right-hand equation, add pi over 4 to both sides. We get 2x is equal to 4 pi's over 4, which reduces to pi. Did not touch the second term yet, but now we're going to divide both sides by 2, which makes our equation x equals pi over 2 plus n pi, distributing our division on the right-hand side. Nice. Now let's march through some n values. Let's let n equal 0. That gives us x equals pi over 4. That is within the interval from 0 to 2 pi, so I like that one. X equals pi over 2. If you want to put plus 0 pi on both of those, you're welcome to. I'm not going to do that. Slide that up a little. Great, so that's our first n value. Both of those are in. Let's try an n value equal to 1. We have x equals pi over 4 plus 1 pi, and that is equal to 5 pi over 4. That's a good solution. That's within 0 to 2 pi. Over here we have x equals pi over 2 plus a pi. So it's pi plus a half a pi, which makes 3 halves of a pi, which is less than 2 pi's. So I'm going to like our solution on this one too. So that is 3 pi over 2. Great. And then what about an n value of 2? Hopefully you're seeing this coming. When that n value becomes 2, this is going to become a 2, this is going to become a 2, these are going to become 2 pi's, and when you take 2 pi and you add stuff to it, it becomes larger than 2 pi, which in these problems is not good, because we're trying to find solutions that are between 0 and 2 pi. I don't care about stuff that's greater than 2 pi. So I can already tell, because I've done a bunch of these problems before, that I don't even need to do any calculations for n equals 2. Another way that you can know that you can stop with those first 4 solutions is when you really come to terms with this. And what this tells us is that we're going to have 2 times b solutions here also. So when when b was between 0 and 1, for example 1/2, I took the 2 solutions that I might have had, I cut it in half, I only had 1 solution. With the other instance, which is the one that we're working on currently, where our b value is a 2, we can take our 2 potential solutions and multiply them by a b value of 2, and we're going to get 4 solutions. Well, one, 2, 3, 4. I already have my 4 solutions. That's another way that I should know or could know that I can stop and I don't have to try that n value of 2. So maybe you just put a note in here next to this n value of 2 that says causes x values to be larger than 2 pi. And then put a sad face at the end of that, maybe. And we can write our solutions as a set. And this is just a set. It's a list of numbers. If you're typing these in online, you probably don't even have to put these set braces. It's just asking you for your solutions separated by commas, and you can type them in any order you want to. At least in my experience, the different learning management systems or platforms that I've used have not required an ordering of my final answers. But you should know your software better. And I'm going to type those in as final answers. So this is a change in topic again. So what I'm going to do is I'm going to put a cut right here. And in order to watch the solution processes for problems like this, just click on that link that's just below me, and it will take you to part 2 of this video. See you there.